Hi everybody, welcome to another video in Calculus 3, section 16.5. We're still doing triple integrals, but this time we evaluate the triple integral in cylindrical coordinates or spherical coordinates. So first, cylindrical coordinate, of course that comes from a cylinder. So apparently this is nothing new in cylindrical coordinate. So first of all, cylindrical coordinate, we still doing triple integral, meaning that we still have dx, dy, dz, or what we evaluate is dv. So we have three components, x, y, and z. So if we have any other coordinate, it have also be three components, and those three components will be as follows. Z will be the same as in rectangular coordinate, so the z will be the same, and x and y will be replaced by r and theta. So pretty much we have polar for x, y. So we have original rectangular, we have x, y, and z. Now to cylindrical. X, y becomes r theta, and z is still z. Right. And all of that still the same way we define. R is the distance on the xy plane to the pole, and theta will be from the positive x-axis. So as mentioned before, xy here to r theta. So this is just like rectangular to polar. So r theta here is similar to polar coordinates. Right. And of course all of that's still the same, but we'll get to that in a minute. Right. So r again is a distance on the xy plane from the pole to the pole, and theta is the angle from the positive x-axis go counterclockwise. Right. Now identify and sketch the following set of points in cylindrical coordinates. We have r between 1 and 3, and z is between 0 and 2. We don't have theta here, meaning theta could be anything. So what we will have the radius r is between 1 and 3, and z is between 0 and 2. So we talk about a cylinder. I mean, not a cylinder. A cylinder with a hollow region. Right. Next we have r, theta, and z, where z is equal to 1 minus r. So if we draw the coordinates, just r and z, r, and then z, we have 1 minus z equal to 1 minus r. But it's not just that. It of course extended further than that. And then we have r is between 0 and 1. So if we just draw z and r, that's what we have. But we need to draw this in 3D. Z equal to 1 minus r. But r is not really the x-axis or the y-axis, so that could go around and around. So actually we will have z to the x-axis. So in this case we have z equal to 1 minus x, and z equal to 1 minus y, and then on which we trace a circle. So what we have here is a cone. It is a cone. Radius 1 and the height is 1. Yeah, so it's a cone. Right. Now, convert between rectangular to cylindrical will be the same as rectangular to polar. We have those two, the same thing as those two, and those two, the same thing as polar. Z is still Z, so there's nothing new here. Right? Z is still Z, X is R cosine, and Y is R sine. So exactly like what we had before. So there's a point. The Z is still the Z component. And then we have X adjacent to the angle. And then Y will be opposite to an angle. And the hypotenuse is that. So there's nothing new here. Right. So in terms of integral, is there anything different here? Right. So let f be continuous over the region D. Then f is integrable, and the triple integral is evaluated in this case. So there's nothing new compared to a triple integral. So we have this. Here we have the function of x and y could be in terms of r and theta, because when we have the integral, whatever outside of it will be treated as constant. So the limit can depend on the variable on the outside. And don't forget this is r here, because r dr d theta is the same as dA or dx dy. Right. And if we group it here, so the variable r depends on the variable on the outside theta. That potentially, that's what we have. Right. Now let's evaluate this integral. Right. Evaluate this integral. We have triple integral in rectangular coordinates. So first, if we write, it will be like this. Z is in the inside, right? So the limit is 2 is for Z, and 1, -1 is for Z. So on the top we have Z equal to 2. And at the bottom, Z equal to -1. So that, and it is bounded on the side by this equation. Right. So what's that look like? Next, this is dy in the middle, so we have y equal to. So we have y equal to plus or minus square root of a minus x squared. I will square both sides. Y squared equal to a minus x squared, or x squared plus y squared equal to 8. So that is a circle radius 8. I mean radius square root of 8, sorry. Square root of 8 is 2 square root of 2 square root of 8. 2.8 something. So we talk about this disk. The one above is y equal to square root of a minus x squared. The one below, y equal to negative square root of 8 minus x squared. And then finally, the x go from 0 to square root of 2, which is the same as square root of 8. So apparently we only go from 0 to 2, so we'll talk about this half of a disk on the right hand side. Right. Now, if we want to write everything in polar coordinates, then the z will still be z. Right. But for this region R here, we can say radius R between 0 and 2 square root of 2, and theta go from negative pi over 2 to pi over 2. That will be the limits for R and theta. So if we want to rewrite that, that is fine. So in fact I will do that. The limit of the dy dx in y and x will replace by theta go from negative pi over 2 to pi over 2. That is limit for theta. And the limit for R between 0 and 2 square root of 2. And then the z limit is still the same thing. Z equal to negative 1 to z equal to 2. 1. X squared plus y squared. Of course it's equal to r squared. And then the dz and then most importantly the dy dx is r dr d theta. So pretty much we convert to polar on xy, where we keep the z constant. Later on it does not necessarily be xy to polar. Essentially we could do something like we go x, y, z, and let's say we're going to keep the y, but the x and z together is going to be r and theta. So potentially that could happen. We keep one of them in the rectangular, the other two turn into polar. In this case we turn x and y to polar, and that's what we have. Right? Go from negative pi over 2 to pi over 2, and r go from 0 to 2 square root of 2. So that's what we have. Now what we have here is the limits are constant. The function here, note that the function we talk about is this, and then the r here as well. So the function actually is separable, so we can put all of them together, each variable together. First of all, I'm going to put the z, and there's no function for z. And now let's group r. R equal to 0 to square root of 2, and we have 1 plus r squared, and then dr. Yeah, with this r, the substitution is a lot easier to do than without it. And finally, we're left with theta. Right, so that's what we have. Let's see if that integral turn the middle integral turn into anything nice and even. I highly doubt it because of 2 square root of 2 or square root of 8 if you will, and then we have square root of 1 plus x squared times x dx. Oh, actually, yeah, 26 over 3, so it's not that bad. So I have 26 over 3, and that is easy to do, so yeah, because 2 square root of 2, so it's 8 plus 1 is 9, so in the square root that should come out nice and even, so it's turned out to be 26 over 3, so yeah, or we use substitution. This should not be a problem, the integral here. Let u equal to 1 plus r squared, then we have r and all that, but the integral will be z from negative 1 to 2, the middle integral 26 over 3, the last integral theta from negative pi over 2 to pi over 2. So we have z from negative 1 to 2, so put in 2 and put in negative 1. Subtract them, and then 26 over 3, and then pi over 2 minus negative pi over 2. So negative, that's a plus. So we have 3, 2 minus negative 1, 26 over 3, and then pi over 2 minus negative pi over 2, so that's just pi. Cancel out, we have 26 pi. It's not that bad. Right. So what we have is keep the z, x and y turn into polar with that limits. Right. Now, second example. Find the mass of the solid region bounded by the paraboloid. So out the top by the paraboloid, at the bottom by z equal to 0. So the bottom z equal to 0, and on the top we have z equal to 4 minus r squared. Right. So remember one thing I said on triple integral. If there is anything like this where we can set up the limit using one variable between the limit between two surfaces, that's what we go first. In this case we have z equal to 0 to z equal to that. This one we write the mass be triple integral, but the one from the inside will be bounded by these two functions, z equal to 4 minus r squared and z equal to 0. And then there's a function in the middle though. Just for now, let's just write a function of r, theta, and z. So first we have take care of the limit z. On the outside we'll have dy and dx. We don't know what that will be, so let's just write dA. Right. Now we take care of the limit between two surfaces, and now we just worry what will happen on the outside of x and y. So we just look on the xy plane. So what actually we have on the xy plane? So xy plane is when z equal to 0, and so we let z equal to 0 here. So we find the intersection. Z equal to 4 minus r squared, and when z equal to 0, so for r squared is equal to 4, or r is equal to 2. So we have this, which is a disk radius 2. Like I said, that will be determined. By the way, for the disk we can write in rectangular, but it would be much better if we write in polar corner. So for this disk, we can say the radius r go from 0 to 2, and it go 1 complete revolution, so 0 to 2 pi. So we will have integral from, right, worry about that later. Let's just write the integral from the inside. Z equal to 0, z equal to 4 minus r squared. The function is 5 minus z dz. The dA, notice that is not just dx dy. It is dx dy, yes, but if we're going to write in polar, don't forget r dr d theta. Those are equivalent. And the limit for r between 0 and 2 and theta will be from 0 to 2 pi. Once again, we can use the Fubini theorem because the function inside 5 minus z and r, those are separable, and no, we cannot. Sorry, never mind. Don't use Fubini theorem because the limits here is not constant. So cannot use it. Yeah, we can do that for r and theta, but because of that, it's not constant. Right, derivative with respect to z, we have 5z minus z squared. So that is the integral. Z squared by 2, sorry. So that is the integral of 5 minus z with respect to z, where z go from 0 to 4 minus r squared. And notice that we still have r here, dr d theta. Right, next, let's put 4 minus r squared here. So we will have 5 z is 4 minus r squared minus 4 minus r squared square over 2. That's what we put in 4 minus r squared, and then put in 0 here, we have nothing. So that's all we have, r dr d theta. Now the limits are constant. We can use Fubini theorem now because all the function here only depends on r. So let's group all the one that have r in it. So we have the limit and all of that associated to r, and then we just have theta from 0 to 2 pi for d theta. And then we have the function 5 4 minus r squared 4 minus r squared dr theta equal to 0, theta equal to 2 pi d theta. Right, so be just like that. Right, once again I'm running out of space, so I'm just enter the whole thing here. By the way, this is a polynomial, the limits are constant. So we should have a nice and even answer. Right. 5 4 minus x squared. I just use x instead of r. And don't forget, wait, did I forgot something? I forgot to multiply by r, which is x in this case. Close x. Yes. Right. 4 minus x squared 2. That looks right. Once again, this will be a fraction, 44 over 3. And that from 0 to 2 pi, so theta 0 to 2 pi, so that's just 2 pi. So we have 88 pi over 3. Right. Next, we derive the formula for the area of the inverted cone with radius a and the height h. So we have the cone inverted. The radius is a, the height is h. Right, so what will be that formula? Right, so what I'm going to draw is just on the coordinate here, the equation though. So we need to set up a bunch of limits. So on the top is easy because the height is h. So we can say the top equation, talk about that, is z equal to h. The plane parallel to xy plane and the height is h, so z equal to h. That is the top equation. Now, the side of the cone, how do we write that? Right. For that, we think about the height is h and the r is equal to a. So this is h and this is a. We talk about z and r. Now, this equation of this line is z equal to, just rise over run times x, instead of x is r. So the equation on the side is h over a times r. So on the side, has R on it, so it will turn around all way around. H over A times R. And after that, on the XY plane, we will see just the circle of radius A on the XY plane. Right. Now with that, so we write the volume equal to triple integral, where the inside most go from Z equal to H over A times R to Z equal to H. This calculate the volume. Sorry, this is a typo. The volume. So we will have the function just one here. So we have dz in the inside. So we'll take care of that first. What we've left will be just x and y or r and theta. Doesn't matter. But on xy, we have a circle of radius A. So on the xy plane, we just have a disk of radius A. So we're just going to write dA or dx and dy, which to be determined later. But we know the limit inside though. dA now can be written as r dr d theta. Now this is this radius A, so for that one, r between 0 and A and theta 1 full revolution, 0 to 2 pi. So integrate this, there's no z here, so evaluate that would be just z, or from h over a r to h. If it's clear that we just substitute to z, we don't need to write z equal to. Here we have r dr d theta. We substitute h in here, and then substitute that in. Don't forget there's an r. Now you guess it. Limits are constant, function separable, Frobenni theorem again. Let's group all of that. The constant limits, the function are separable. There's only if depends on r. So we can just group. You just group the part that have r in it. And then the part that have theta in it. Right. Cannot use calculator here because there's a. But I'm going to multiply r to be hr minus h over a r square dr, and then integral of that will be just theta from 0 to 2 pi, or just 2 pi. Right, now integrate. hr will be h r square over 2, and this is h over a r cubed over 3. We evaluate from 0 to a. After that, we multiply by 2 theta. I mean 2 pi, sorry. Now, substitute in a, here we have something. Substitute in 0, here we have nothing. So first, substitute in a, we have h over 2 times a squared, and then minus h over a cubed over 3 multiplied by 2 pi. And a cubed and a cancel out, we have 1/2 h a squared minus 1/3 h a squared. A cubed and a cancel out, we have a squared, and then 2 pi. Right, those two are the same. 1/2 minus 1/3 is 1/6. So we have 1 over 6 h a squared times 2 pi, so give us 1 over 3 pi a squared times h. So that is the volume of inverted cone. Now if we turn it upside down, if we have the radius a and the height h, the volume indeed is 1/3 the base area times height, and 1/3 the base area is pi r squared. But we won't want to use a, don't want to use r, we use a instead of r, h. So this is the volume of the cone, right? And that is consistent to what we have. Yeah, the reason I inverted it so the equation is a lot easier to do than it will be a lot easier to write than this equation. Yeah, but that's what we have. Right, so like I said, there's nothing new. Just pick one of x, y, and z. In here we only have z, but later on or in real life we can choose x to be constant, to be the same as x, and we convert the yz into polar. So keep one of them, the other two convert it to polar. Right. What's next is spherical coordinate, which is new compared to what we have earlier. Right. So I will relate this to something that hopefully that you know already. So once again, the point is in R3. So we have whether we have x, y, z, or z, r, theta, and z in three-dimensional space, we need, I think, any point must be represented using 3 components. And one of those, we define rho. So that is the Greek letter rho. And this is the Greek letter. This one is rho, and this one phi or phi. I just say phi, and this is theta, of course. So the theta here will be the same as polar. Theta here is the same as polar, and then the rho and phi, the rho and phi, will be different. So we define rho to be the distance from the origin to the point. So rho now is the distance to the origin. And then the angle phi here, or the angle phi here, going from the positive z-axis to the ray OP. So that is phi. And theta is the same as before. So apparently So we have those three things. Rho is the distance, so they have some measurement. Phi or phi and theta, those two is the angle measure. So we have two angles and one radius, one distance. So what does that sound like? Right. So it has nothing to do with math. I mean, something to do with math, but just go to geography. So, let's say we have the Earth. Here's the equator. Of course, there will be another latitude. There will be the North Pole. And there's the South Pole. Connecting the North and the South Pole, we have a bunch of longitude. Of course, on the other side as well. Right? Right. Once again, the line that connects from the north to south is called the longitude. And the line that goes like this is called the latitude. The way I actually remember this is, as you see, the latitude on the top is very small. At the bottom, at the equator is the biggest. The longitude, all of them have the same length. So all the longitudes have the same length. So from the north to south, all of them have the same length. Right, what's so special about it? There's a special longitude that go through a place in London, in a town named Greenwich. So if you heard about that, that's called the GMT, which is Greenwich. Hope I spelled it correctly. Greenwich Mean Time. And that is for one of the longitude. And that longitude have a special name called the Prime Meridian. Now, probably they don't use Greenwich Mean Time. They could use UTC, Coordinated Universal Time. Kind of the same thing. So we have that. The opposite to it, on the other side, is the International Daylight. So passing that with the points opposite on the International Daylight will differ by almost 1 day. Right. So the Greenwich Mean Time, or the prime, the longitude that go through Greenwich, all represent the coordinated universal time on the Prime Meridian. That is called the 0 degree. Anything on the right side of it is east. Anything on the left side is west. And from the Greenwich Mean Time on the Prime Meridian, you go this way, go to International Daylight. We have 180 degree east and 180 degree west. So 180 degree on one side, 180 degree the other side. Together is 360 of those. Now, so that is the longitude. The latitude, special one is the equator, and then we have everything parallel to it. So we have like that, latitude. Right, so from the equator, we're going up is north. If we go down, it's going to be south. The North Pole is 90 degrees. So we go from the equator up to the North Pole, 90 degrees from the south pole to also 90 degrees. So 90 degree up, 90 degree down together is 180 degrees. So the latitudes, there are 180 of them, the longitude 360, right? So that's what we have. So in here we represent the phi angle. However, the difference between this geography and the spherical is that we no longer going from the equator up and down. We always start from the North Pole and we go down. North Pole is 0 degree, equator is at 90 degrees, South Pole is pi or 180 degrees. So that's what the angle phi is between 0, which is the North Pole, and pi, which is the South Pole. So, and then theta is the same as before, so we'll go from 0 to 2 pi. And this is the relation. Right. Now, so that's nice and all, but need the ruler. Let's draw this. Again, what I draw here is the Z and the R. Now, if we do that, and let's say there's a point somewhere in here. If there's a point in there, we'll calculate the distance from that point to the pole. We're not going to use R anymore. We have to use the Greek R. So that is rho. It's not P. P written like this. So the rho more like start from the bottom like that. So that distance is rho. And also the theta. This is go from the positive x-axis. We're not doing that anymore. We define the angle phi to be from the positive z-axis and going downward. Right. Now, think about this. Essentially, this is what we have. We have x, y, and z in rectangular, right? Now, what we do is we're going to take x and y, replace that into r and theta. And that's called cylindrical coordinate. And after that, we replace r and z to rho and phi. And then we still have theta. So what do we see here? So once again, x and y, or we take two of those, convert to polar. After that, there are two measure of length. Convert those two, remain into rho and theta, which is a distance and an angle. So actually, think about that spherical coordinate. It's just like the double of the polar coordinates. By double, we mean we take two of them, replace to r and theta, and take r and z, replaced by rho and phi. Right, so that's called the double polar. I'm not sure if anybody call that, but it's what it's actually how it is. Two of them will go into a length measure and an angle measure, and then we have that and z convert to rho and phi. So this is the double polar. Anyway, so if we have this relation, this is z adjacent to phi, so z equal to rho adjacent to it And then we have this opposite to it, which is R. Same thing as here. Is rho. Opposite is going to be psi. Fine. Now all of this is nice to know, but we'll get back to this in a minute. Now, let's go back to what we established earlier. We have x, y, and z in rectangular coordinate, right? Now in polar, z is still z. But in polar, we have x is r cosine theta, and r sine theta. That is in cylindrical coordinates. Now, we have r equal to rho sine phi, rho sine phi. So I substitute in for this r and this r. So I have rho sine of phi, cosine of, this should be theta, sorry. And then sine theta. And then z, we already established that is rho cosine theta. Rho cosine phi, sorry. Right. Yeah. So that's exactly what we have here. And also, we have x squared plus y squared equal to r squared. Now if we add z squared on both sides, that's what we have. And in this triangle, r squared plus z squared is equal to rho squared. So, now, like I said, think about this as the double polar. We go to polar first, take with two of them, and then whatever we have r and z, convert that to polar again. So it's always nice to draw this out. And the difference here is that the angle phi is from the positive z-axis coming down, as opposed to from the r going counterclockwise, and rho is the distance. Right, so those are the relation. So it is much easier if you understand this than try to memorize this. Right, so that's all we have. Moving on. I spread the following set in rectangle coordinate and identify the set. So we have rho. So we need this to be in rectangular coordinates, meaning that should be in terms of x, y, and z. So we have cosine, right? So take a look at this. Look like if we have cosine and we multiply by rho, that gives us z. So that's good. Why don't we do that? Multiply by rho on both sides. Can multiply by rho on both sides. So that gives us rho squared equal to 2a. A is a constant, and then we have rho cosine of phi, and this of course is z, and rho square x squared plus y squared plus z squared. So bottom line is what we have is x squared plus y squared plus z squared equal to 2az. Move that to the other side, complete in squares. This is the equation here. By the way, that looks like a sphere, but it only goes from 0 to pi over 2, so it might be the upper hemisphere. Right. What is the angle? Only from 0 to pi over 2, so be careful with that. So we only know this is going to be a sphere, not a sphere, more like a bowl. Never mind, this is a sphere. So what is different between a sphere and a bowl? A sphere is only on the surface. The bowl is include the interior, and it's only half a sphere, not the whole sphere though, half of a sphere. So the upper hemisphere, if you will. Oh, just half a sphere. And then because rho is equal to 2a, so that's a sphere. Right. Actually, if you want to, we can actually graph in polar. Remember, this is like a double polar. Let's say a is equal to 1. Yeah, so actually, what if we only go from 0 to pi though? Pi over 2. Yeah, so kind of a hemisphere. But that is with respect to the, so phi. So think about that, we go from kind of half a sphere. But then you go like that, but then you go around. So actually it is the whole sphere though, because we have that and rotate about 2 pi out. So I cannot turn the calculator sideways, but on the z-axis it should be like that, because z equal to something here. Right, anyway, not important. Right, here we have rho equal to 4 secant phi. Secant is 1 over cosine. Cross multiply, we have rho cosine phi equal to 4, and that is of course z. So we have the equation z equal to 4. And here we have the angle from 0 to pi over 2. So actually this will extend it forever. Think about this. If we have the point here, then we have an angle phi from the positive z-axis to that point. The point way out here, the angle is bigger. If we go all the way to pi over 2, it cannot get to pi over 2. So it can maybe just less than. Because it is pi over 2, it will be parallel to, it will be on the xy plane, which is not z equal to 4. So this extended in every direction, z equal to 4. So extend in every direction. And theta go from 0 to 2 pi, so it go complete revolution. So just like, it's not, maybe not that, but more like a disk extended indefinitely. Right, so now how do we evaluate the integral? So triple integral in spherical coordinates. f be continuous over this region. So the difference here is that the phi is bounded by two constant, theta bounded by between two constant, and rho is bounded by two function of phi and theta. So what new here is the dv, dx, dy, dz, or dz or dr d theta is equal to all of this. So that is dv. So the note here is dv is equal to rho square sine phi d rho d phi d theta. So in section 16.7 we actually prove why it is that way, but for now we're just going to use it. Right, next, evaluate this where D is the region in the first octant. So in first octant between two spheres of radius 1 and 2. So look like that. So let's write the limit for the region D. We know rho will be from 1 to 2. And then the angle phi or phi, it goes from 0 to the equator, so 0 to 90 degrees. And theta, only first octant, so on two-dimensional plane is only 0 to 2 pi, pi over 2. Only first quadrant in xy plane. So that's what we have for D. Now we write the triple integral. X squared plus y squared plus z squared. That sounds familiar, right? That is rho square, right? So we have rho square to the negative 3/2 yeah, that's it. That's the function. And then the dv is that rho square sine of phi d rho d phi d theta. Right, let's write one more step. Rho square to the negative 3/2 power to another power. We multiply them. So rho square to negative 3/2. We multiply the exponent. 2 and 2 cancel. We have rho to negative 3. And then we still have rho square sine phi d rho d phi d theta. Now the limits in the inside, d rho from 1 to 2. Phi from 0 to pi over 2. And d theta from 0 to pi over 2. Right. Rho to negative 3 times rho square is rho to negative 1. I said if it's clear to the context, going to group that. Rho times rho to negative 1 sine of phi d rho d phi d theta. Right. Once again, all the limits are constant, so I'm going to use Forbinian theorem. First, let's group all the d rho, limit from 1 to 2, rho to negative 1, d rho, and then next, yeah, we have that limit. Yeah. So those are term with rho in it. Next will be for phi. Those are limit for phi. We have that, and we have this function. And what's left is just theta. That's pi over 2. So rho to negative 1 integral is ln of absolute value of rho. That goes from 1 to 2. What is the integral of 0 to sine of theta, which is cosine, and 0 pi, so that should be 1. Actually theta. It's free though. It doesn't matter. It's 1. So that integral just 1. Integral goes negative cosine go from 0 to pi. That's easy. And the next is pi over 2. I don't know why I changed the color here, but yeah, multiply. And we have ln of 2 minus ln of 1 times 1 times pi over 2. ln of 1 is 0, so the answer here is just ln of 2 times pi over 2. Right. So that's what we have. Moving on. Next, find the volume of the solid bounded by lie inside the cone, and it's inside the sphere. So we're talking about the ice cream cone. So we have a cone and an ice cream on the top of it. So kind of like that. I'll find the volume of this one. And phi is between pi over 6. So pi over 6, we're talking about the cone pi over 6. So what's that like? So if that is the case, we can take, let's say, tangent on both sides. Because in the spherical coordinates, oh, sine, cosine, never mind. We'll take sine on both sides. Sine is r over rho. Sine pi over 6 is 1/2. Rho's multiply, so we have rho equal to 2r. sorry, this is not R, but whatever this is, it's going to be twice as long as this. So we're talking about the cone. It's not important though. Right, and so we will set up the limit. Now, if we can set up similar to, we can do this in rectangular, would be a little more difficult, and cylindrical a little less difficult. But if we want to set up the volume for this one using spherical, it will be extremely easy. So we're going to have V equal to that's what we have. This is the ice cream cone. So we actually talk about the volume though. Right. Now, in spherical coordinates, dv is rho square sine phi d rho d phi d theta, and the rho in this case, if we go from inside, look outside, the only thing we see is the sphere. We go from the origin, so rho go from 0 to 4. And phi, we go from 0 to pi over 6. And we go one complete revolution all around. So theta from 0 to 2 pi. So put all of this together, we will have 0 to 2 pi for theta, 0 to pi over 6 for phi, and 0 to 4 for rho. And we have rho square sine phi d rho d phi d theta. And what next? You guess it. Constant limit function separable. That's called for Fubini theorem. So we have this for rho. And we have this for phi. And what's left is theta. Right, the first one will be 64 over 3. Yeah. And sine, I don't think this will come out nice and even. It is in radian mode, yes. Yeah, what's that like? Right. Integral of sine is negative cosine. Let's go from 0 to pi over 6. And then integral from 0 to 2 pi of theta, just 2 pi. So I have 64 over 3. Put pi over 6 here, we have negative cosine of pi over 6. And then cosine of 0, negative. Negative again, cosine of 0, 2 pi. So bottom line is we have 64 over 3 times negative square of 3 over 2 plus 1 times 2 pi. Square root of 3 over 2. Actually, that's negative. Plus 1. Yeah, so those are the same. Yeah, so that's what the answer is. Next, evaluate this in spherical coordinate in the unit ball. So the unit ball, row between 0 and 1. Find from the north pole to the south pole. Theta all the way around. So that will be a limit. Will be easy. So let's write this. Z d dv. So triple integral. Z. What is z? So of course I can look it up real quick, but I just derive from memory. Z vertical axis, and then R, we have angle phi here. Z is adjacent to the at angle phi, so Z is adjacent is cosine. And then we have the dv is always rho square. In section 16.7 we will prove why there's rho square sine phi in here. And then d rho, d theta, d phi, d theta. By the way, in some books they're switching the role of theta and phi. But here we will do d phi, d theta. Limits, extremely easy. For rho, the inside from 0 to 1. For phi, from 0 the north pole, pi the south pole. And theta all the way around. Right. Rho square times rho cube, sine cosine. We have d rho, d phi, d theta. Now let's group them. By group them I mean apply the Fubini theorem. For rho, and for phi, we can only do this with constant though. Sine, cosine, throw that flashcard away. And then what's left is just d theta. D theta, there's nothing. I showed it to that. So let's see the middle. The first one is easy, 1/4. I hope it's come out nice and even. Oh, even better, 0. So after all of that, the middle is 0, therefore this is equal to 0. It doesn't matter what the rest of them are. Right, so why is that? So we're talking about a unit sphere, right? So it is perfectly symmetric. We have what we can have the z function in there. For the upper hemisphere, the z is positive. For the lower hemisphere, the z is negative. So pretty much it is symmetry some way. The one above is positive, the one below the xy plane is negative. Because of that, they cancel out. So that's why that is equal to 0, and that makes sense. Right? Yeah. Same thing if you have x or y, just x or just y in there, it should behave the same thing, because it is perfectly symmetric. For 1/2, we have x values, so have some positive, and there's a point opposite to that, so they just cancel each other out, and that go to 0. Right. By the way, if it is not 0 and we have to integrate that, remember the power reducing. I throw that flashcard away. Cosine square is 1 plus cosine 2a over 2 sine square 1 minus cosine 2a over 2, and sine and cosine is going to be sine of 2a over 2. Multiply 2 on both sides, that is the double angle formula. Right, so what summary at the end here, I'm just do actually some example. Let's first talk about the sphere. Of radius a. The equation in rectangular coordinates will be x squared plus y squared plus z squared equal to a squared. That is your sphere. If we have less than or equal to, we have the bone. Cylindrical coordinate, we're going to take x squared and y squared, replace that by r squared. So in cylindrical coordinate we have this. And then when we combine those together in spherical coordinate, we will have rho squared equal to a squared, or rho is equal to a. So that is for the sphere, Now let's talk about the cylinder. Let's just say this is the circular cylinder. There's a here, and this is extended forever. So the equation is x squared plus y squared equal to a squared. Z doesn't matter because this cylinder extended along the z-axis. In cylindrical coordinate, that's the reason we call this cylindrical coordinate. X squared plus y squared equal to a squared. So if r squared equal to a squared, or r equal to a. Now if r is equal to a, what r is equal to? So z is adjacent to the angle phi, and r is opposite to it, so r is rho sine of phi equal to a, right? R is equal to rho sine phi. And so we write like that, or we can divide by the sine phi, a over sine of phi. What next? Let's talk about a cone, like the inverted cone. Again, radius a and height is h. Right. Let me just find out what did we do for that problem. Where's the cone? Right here. Right. That equation is z over h over a times r. So we have z equal h over a times r. We don't really have r here. We have square root of x squared plus y squared. So z equal to h over a square root of x squared plus y squared. And here the cylindrical coordinates be z equal to h over a times r. And now if we want to write this, we take z divided by r. And z divided by r, what is that? Yeah, I actually wish this worked, but let's just rewrite this differently. So, sorry. Z equal to h over a. R is in term of rho is rho sine of phi. So that is r, rho sine phi. And then we divide z by p, or z by rho, or rho by z. Or we divide this over, so we have z over rho equal h over a sine of phi, and z over rho is cosine. So cosine of phi equal to h over a sine of phi. Right. And finally, just a paraboloid. Equation z equal x squared plus y squared, but x squared plus y squared is r squared, so z equal to r squared. Equivalently, we have z equal to rho r squared. Z is adjacent to rho, so adjacent to phi. So z is cosine and r is sine. This is where, right, we can simplify from here. But yeah, so the certain object we can spread in any form, rectangular, cylindrical, or spherical. But sometimes some form is a little bit better. Usually the cylindrical coordinate kind of a nice compromise, mostly. Something written in rectangular is more convenient than spherical, but spherical sometimes convenient, like those two, like those and the cone. Depends, but sometimes could be complicated. Right, bottom line is it's just a review and the relate between rectangular, cylindrical, and spherical, and as always refer to this. So, and so spherical pretty much is a double polar. So we do one polar for x, y, and then one polar for r and z. Right. So with that, we finish section 16.5, the triple integral. So the next two sections is not about the integral, more like one section 16.6 is about application, and 16.7 is more like theorem. 16.7 is very important. But for now, that is 16.5. Thank you for watching.